So our next speaker is Sara van der Geer from ETH in Zürich, and Sara will talk about interpolation and regression and classification.
Okay, thank you very much for this invitation, for this wonderful workshop. So I'll talk about interpolation. And the motivation is a little bit that you see many algorithms which have zero training error, but still a good test error. So I'm going to look, well, zero test error can only happen if, or small test error can only happen if there's little noise. So I look at the framework will be when there is little noise, and it will be just toy models, regression, and a simple version of classification. So it's with small noise, like in Johannes' talk, so that there the focus is on small noise as a mind setting. Okay, let's see. This is joint work with Geoffrey Chinot, Felix Kuchelmeister, and Matthias Loeffler, and these are my colleagues and students at the ETH in Zurich. And here's the model. Oh, sorry, so it will be regression and classification. So regression just as a starter and interpolation in classification as the main new results. But let's start with regression. So we have a simple linear model. Y is a linear function of x plus noise. So y is an n-dimensional vector and x is an n times p dimensional design matrix. And p is the number of columns and n the number of rows. So there are p variables and n observations. And then there are also p unknown coefficients, which I call beta star, p parameters. And I assume as a normalization that the L2 norm of this vector of unknown coefficients is 1, call that the signal strength. And there's the noise psi, n-dimensional vector, which you don't observe. And it has length sigma, which I call the noise level. So in all of the talk, this noise can be anything, but for the moment, let's not just emphasize any assumptions or whatever on it. So it can be deterministic or random. And then, so if it's random, then this noise level is a random variable, but don't worry about that. But the framework will be that the noise level is small. It's not an assumption, but it's the context I'm thinking of. And what it is a toy model in the sense that I'm going to assume that the design matrix has IID Gaussian, standard Gaussian entries. Okay. So if you want to do interpolation, I'll come back to that. Why do interpolation in the first place? Oh, sorry. We can do interpolation because I'm going to assume that P is much larger than N. So it's a high dimensional model. So you can always interpolate the data. Okay. And then there are many interpolators. And one way you could do it is just take the interpolator. So the vector B, which interpolates the data and which has smallest L2 norm. And this is just like the linear, the least squares estimator, which is written here, where you look at the Gram matrix, X transpose X. And this Gram matrix is not invertible. So instead you take, instead of inverting it because you can't, you take the more Penrose inverse. And then you do this usual least squares formula, and then you get this minimum L2 norm interpolator. And yeah, so that's a very bad idea to do it this way, because this L2 interpolator, it just estimates the zero factor. This is quite obvious and well known, so it's not something I invented. But just to realize that you can't do L2, minimum L2 interpolation, we look at minimum L1 interpolating instead. So if you do this minimum L2 interpolation, you get the difference between the estimator and the vector you're trying to estimate, you can decompose it into a bias and a variance term. And what this estimator is doing, it just projects the true vector beta star on a low dimensional space. And then the residuals are actually this vector beta star again, because you only project on a very low dimensional space. So the bias is like the vector beta star itself. And the variance behaves like n divided by p. So I'm assuming that this ratio is going to 0. So the variance goes to 0. So even if you don't have noise, minimum L2 interpolation doesn't make sense. Which is actually why people like Candace and Donohoe invented basis per shoot. So we do different interpolation. Okay. Where am I? Let's go to the next slide. So just a few words about why interpolation. So if there's little noise, interpolation could make sense. But typically we do not know the noise level. So we do not know whether there's little noise or not. Maybe we do it because we know how the data are generated, but in general, this is hard to find out. So you can try to estimate the noise level or using regularization, and then from that estimate the noise level. And one way to do it, to regularize using the L1 norm. So that's the lasso, which is just least squares. Sorry, what was that? Participants can now see your application.
We can only see your slides.
Oh, good. So that's good, right?
Yeah.
Everything's fine.
Yes.
Okay, so the lasso is, you all know, least squares estimation with a penalty, which is the L1 norm of the coefficients times a tuning parameter lambda. And then, of course, the question is how to choose the tuning parameter. Now, as a sort of byproduct of this interpolation theory, we get a result which says, well, at least gives a bound if you choose your tuning parameter too small. So that may be of interest. I don't know if there's much work on that. So if you're in an unsafe regime where your tuning parameter is too small, we also get some bounds. But still, so the tuning parameter of the lasso depends on the noise level. And if you don't know the noise level, you don't know how to choose it. So as a remedy, there is the square root lasso, invented by very famous people. And there you can take a universal choice of the tuning parameter. And then there's theory for the square root lasso, which is like the theory for the lasso, but it depends on an assumption on the L1 norm of the true vector of coefficients. It should not be too large. And the problem here, it depends on the noise level, this assumption. So if I have a very small noise level, this is not a nice assumption. And it depends on this square root n over log p, which I wrote in red because it occurs everywhere in the next few slides. That's a crucial quantity. But this is a bad assumption. So I don't know if the square root lasso is a good idea if your signal is very small. Then maybe the square root lasso will just do interpolation. Of course, you can also do cross-validation if you don't know how to choose the tuning parameter, which is computationally intensive. And again, there's a lot of good theory for it, but I don't know whether it still works if the noise is small, the theory. So we just do interpolation. And we assume sparsity. I hope you don't mind. So that the number of non-zero coefficients of the true regression coefficients is relatively small, so smaller than n divided by log p, that ratio again. And we don't want to assume anything depending on the noise level. because I'm thinking of a small noise level. So this L1 norm assumption is not what I want to assume. Okay. So if you have a regression model and you do the minimum L1 norm interpolator, that's just basis pursuit. But now we look at noisy basis pursuit. So basis pursuit from Chen and Donohoe, if you have no noise, it gives exact recovery. But if there's noise, you can't get the exact recovery. But what do you get then? And there are papers about it, Wojtacik in 2010, Yu, Lin, and Liu in 2020. So I would say our results are the same as Wojtacik. We didn't know this paper because it occurred in a non-statistical journal, maybe. But anyway, so we have different proofs which allow extensions to other sparsity-inducing norms. But here's the first result. So the idea is as follows: if you do minimum L1 norm interpolation, the L1 norm of your estimator will be bounded by the L1 norm of the truth, plus a term sigma hat square root n over log p. And that's in the high dimensional case. And that result really relies on the assumption of IID Gaussian design. If not, then the bound will be probably different. So this is why we use this not very nice assumption of Gaussian design. Now, because of time, I don't want to go into the proof. But once you have a bound for the L1 norm, you can use empirical process theory to bound the estimation error. And so then you can use kind of standard tools. And if you do that, you get the following result. So assumption on the sparsity, not depending on the noise level. And then with very large probability, the estimation error is bounded by a constant times the noise squared, noise level squared. And so I call the squared L2 norm, I call that the estimation error. And the constants here are universal constants, C, C prime, and C double prime. Okay, so just a little comparison. So if you look at the estimate or the prediction error in a test set, there's always the unavoidable noise. So think of the case where the noise is additive Gaussian noise, independent of the design, just for this particular slide. Then you can decompose the prediction error in estimation error and the unavoidable error. And if you then only look at the estimation error for the lasso, if you take your tuning parameter large enough, you get for slow rates, if you only assume L1 sparsity, you get the so-called slow rate. And if you assume L0 sparsity, so the number of non-zero coefficients being small, you sort of get a squared version of the slow rate. You get an initial square, more or less. And then there's always the unavoidable error. If you take your tuning parameter too small, of course, I'm thinking of small noise, but still you can take it too small. And then you get, well, let's first look at L1 interpolation. In L1 interpolation, you get, instead of, for the slow rates, instead of lambda times the L1 norm, you get the L1 norm squared, which is nice. And you have, of course, the sigma squared. And if you assume L0 sparsity, the rate becomes sigma squared, doesn't depend on the sparsity level anymore. So, and if you have the lasso with a too small tuning parameter, you get something like, well, at least it's a bound. I don't know if it's a good bound, maybe you can tell me. You get something like the interpolation bound and an additional term due to the bias of the panel by using a penalty. Okay, so from this, it's not so completely clear that interpolation is a very bad idea. If the noise is very small, interpolation can be quite okay. Okay, so makes sense. Now let's go to classification. So now y is no longer the real valued response variable, but it's the sign of the regression function. Okay. So it's like 1-bit compressed sensing, except that we also have noise. And then you can think of 2 interpolators, or more, of course. You cannot do logistic regression in this case, because if there's no noise, or if there's small noise, this gets out of balance, like in Johannes' talk. So your logistic regression is not an option here for small noise, because of the log of probabilities going to -infinity. So you have to do something else. So just interpolation is an option. So here's the estimator from 1-bit compressed sensing, which is developed by Plan and Verschienen. So I call it the Plan and Verschienen interpolator, which says, okay, just take a linear combination of the axes such that its sign is the same as the observed sign of your response vector. And then take the one with the smallest L1 norm. But because the sign doesn't change if you make the vector, you scale it a little bit downwards, you can take it arbitrarily small, so you have to normalize it so that it doesn't become arbitrarily small. And the other interpolator will be the max margin interpolator, where you look at the margin, which is this inner product between y and the linear combination. And then you maximize that over all vectors of coefficients. That's also an interpolator, because you'll always make sure that this margin will be positive, because you maximize it. Yeah, so you will have we will interpolate the signs. So now we want to obtain bounds for the estimation error, or for this L2 error. And there are theoretical results for the Plan and Verschienen estimator. But for max margin, I don't know exactly. I haven't seen any theoretical results. It's related to ADA boost. I'll come back to that quickly. So recall, I'm assuming the design is IID Gaussian, and I'm assuming the high dimensional case. I don't know, a few of time. So if you look at the small noise, you can see, of course, like also in Johannes' talk, if the noise is small, the excess risk will depend on the noise. So if you look at misclassification error, it depends on how large the noise is. But in view of time, I won't go into details here, and just look at estimation error, and the unavoidable error is the base error squared in this case. Okay. Then you can do try as a benchmark, instead of interpolation, you can try regularization, something like a lasso type of estimator. Yeah, so this looks like the lasso, except we only have this inner product term and not the quadratic term. And then you can take the tuning parameter independent of the noise. And that gives you, so this lasso benchmark gives you an estimation error, which is not 0, of course, because you only observe the sign. You will always have an error, even if the noise is 0. And it's exactly otherwise like for the lasso. If the vector is L1 sparse, you get the slow rate. And if the vector is L0 sparse, you get the fast rate, where you win sort of a square root. And if the noise is small, you don't even see that there is noise in the rates. Okay. Because it occurs in a multiplicative way. So now let's look at the Plan-and-Verschienen estimator, which interpolates. We get a bound for the L1 norm of the estimator, which is exactly as for the noisy basis pursuit estimator. So it's exactly the same. And once we have that, we can again use empirical process theory. I'm going a bit quick here, but it gives you the rate. Once you have the L1 norm, you can use empirical process theory to get the fast rates and the slow rates for the Plan-and-Verschienen estimator. And I'll give you a table in a moment. And for the max margin estimator, it's related to ADA boost. So if you do the ADA boost algorithm and you let the learning rate go to 0 and the number of iterations go to infinity, it converges to the max margin classifier. And we actually have results which gave a quantitative estimate on this convergence. So it's known. I'll just clip this slide because of the time, but it's known that the ADA boost algorithm converges to max margin. And to have quantitative results on how this depends on the learning rate and the number of iterations. So the learning rate is eta and the number of iterations is capital T. That is we quantified that to see how fast this convergence is. So the max margin or the minimum L1 norm interpolator is actually the limit of the ADA boost algorithm. And there's a paper by Liang and Sur which gives the precise asymptotics, but that's not for our regime. It's the regime where P divided by N goes to a constant. Okay, so you minimize the L1 norm subject to interpolation and subject to that the margin is bigger than 1. And then our strategy was again first to obtain a good bound for the L1 norm of the max margin classifier, and it looks like this. So there's a power of 2/3 somehow dropping in, but actually this bound, I didn't write it, but this is an upper bound and also a lower bound. So we have a tight bound for the L1 norm. And once you have that, again, you get, I'll skip that, you get the result for the estimation error. Yeah, so let's look at the table. So there's the benchmark estimator, which is sort of like a lasso for the binary case. There's the Plan-and-Verschienen estimator and this max margin estimator. And there's always the unavoidable error in the misclassification error. So yeah, the classification error. If you only look at the estimation error, you see that instead of multiplicative, the noise occurring multiplicative, it occurs additive. And otherwise, we see that for the Plan-and-Verschienen, we have under L1 sparsity, the square root here. And if you assume L0 sparsity, you can win a square root, but not if there is noise, at least not in our theory. And for the max margin, we could only prove the rate corresponding to L1 sparsity. And if you assume more, we couldn't prove more. So there's still work to do there. So probably we're not optimal. And in fact, I must confess that we before thought we had proved a better result with a rate 1/3 instead of 1/2. Or I should say 2/3 instead of 1/2. And there we used a paper which was not published and which turned out to be wrong. And then we thought we had repaired it. And now I realize again that it's still not correct. So I have to be careful. But if we look at our simulations, we see actually that the rate of convergence is more like 1/3 in the exponent and even yeah, in 1/2 if you have no noise. So these are the simulations, and you see that the estimation error decreases with the power 1/3, at least in these simulations. It's kind of hard to do simulations because there are so many things to choose, like the sample size and the number of observations and the sparsity of the true vector. We proved the results for arbitrary noise, so it can be adversarial noise, and this is just sign flips noise. And we think it behaves like the noise to the power 1/3, but we have a worse exponent there in the theory as yet. But so there's still work to do. Under L0 sparsity, we get a faster rate in the simulations than we get from the theory, really much faster, the one which you would expect actually under, that you would win a square root somehow. But we don't know how to prove it for max margin, but we do know how to prove it for the Planin-Verschienen estimator. And also the margin, the bound we have for the margin, which is this gamma downstairs, that's tight. And that behaves like the exponent is 1/3, and you actually also see that in the simulations. Yeah, and so what we did, of course, is also look how the ADA boost itself behaves if your number of iterations is not infinity, and you see that this is this dashed line down here. You see it sort of they behave similarly indeed in the simulations. So a conclusion. So if you look at regression, if there is little noise, interpolation may be as good as the lasso. And in classification, you will not have, if there's no noise, you still have an error, and this error can be, the dominating error can be larger than the noise. So if the noise is small, interpolation in classification can be a reasonable thing to do. And what we still are working on is this exponent. We have 1/2 or 1/4, depending on what you look at, but we want to improve it to 1/3. And that's really, yeah, still, I guess that will be done at a certain point, because if we keep on disagreeing about things, we are 4 people and take some time to convince each other that it's finally correct. But we can just sort of use the same theory as in the line segmentation problem. But it's not exactly the same, so we still have to do some work. And the lower bounds, we don't have lower bounds. We have lower bounds for the L1 norm, but not for the estimation error. So there also we still have to do some work. Okay, thank you very much for your attention. This is what I wanted to share with you. I see there's one chat. Let's see.
Thank you very much, Sara. That was a
thanks.
really interesting talk. Are there questions? Maybe I can start with asking, can you extend some of what you told us to sparsity, not in beta, but in some transform of beta, like, I don't know, total variation, for instance, or something like that?
Oh, total variation would be good, but then so we have this step from going from the L1 norm to the empirical process theory. And then, of course, the empirical process with total variation behaves much better, but the L1 norm will be much larger. So it will be sort of, we believe you will get similar results. Yeah. And we do have some results for if you do, the matrix version with the nuclear norm and so on. So we have results for that, and square root, sorry, no, what's it called? Group lasso. But indeed, total variation, it's a bit difficult to, if you just do one-dimensional total variation, it's kind of, yeah, you just sort of almost trivial what you get. So because the total variation of the noise typically is infinite or very large, I would say, and the sample size, something like that. So, but for bounded noise, I can do something, sure. Yeah.
Okay.
Thanks. Nice question.
Thank you. Let me just check again the chat and also the audience. Are there any more questions? Okay, Sara, I think everyone is happy. Thank you so much.
I'm happy too.
Thank you.
Thank you.